Chapter 4: Work, Energy, Power and Machines. Now, like force, the words work and energy have a variety of connotations in common language. When we say work, we sometimes mean exercise. Other times, we mean a place we go every day and do something and get paid. Energy is even more convoluted. We might say that today we have no energy, meaning we feel tired. Or we might use the word in a more metaphorical way, saying that a person or a place has good energy. But in physics, these words mean something very specific. Let's start with work. Work is defined as action done on an object whereby an applied force causes a displacement of that object. For example, pushing a block on the floor. Work is equal to the magnitude of the applied force times the displacement of the object. So it has the units of force, that is newtons, times distance, that is meters, giving us the units of work as Newton meter. This is usually called joules. A joule is therefore the work done when a force of 1 Newton moves through a distance of 1 meter. So, work is said to be done only when an applied force succeeds in displacing a body. And therefore in these two illustrations, although the gentleman on the right side may get tired because of pushing the box, technically he has done zero work. In addition, only the components of the force that are parallel to the displacement are considered to be contributing to work. Consider a force applied in pulling a box as shown here. The force makes an acute angle theta with the direction of displacement. Here, the total amount of force is not being utilized to make the block move. Only the component of the applied force along the direction of displacement is responsible for the motion of the block. Let's call it Fx. We have a right-angled triangle. Theta, F and Fx are related by cosine. That is, cos theta is equal to Fx over F, meaning that Fx is equal to F cos theta. So, F cos theta is the force responsible for motion of the block. Therefore, the work done here is equal to Fd cos theta. In the expression of work, force and displacement are vectors, but work is a scalar quantity. Work done can be positive, negative, or zero. Work done is said to be positive when the motion of the object is in the direction of the applied force, or when theta is less than 90 degrees. For example, when an object falls to the ground, work done by the gravitational force is positive. Work done by a force is negative if the motion of the object is in the opposite direction to the applied force, or theta is greater than 90 degrees but less than or equal to 180 degrees. If you lift an object from the ground, the work done by the gravitational force is negative. Work done is zero if the applied force is perpendicular to displacement. For example, when a block is moved along a horizontal surface, the displacement is along horizontal, while the gravitational force, which is essentially the weight of the block, acts vertically downwards. In this case, work done by the gravitational force is zero. If the applied force varies along a given distance, then the work done can be obtained by plotting a graph of force against distance and determining the area under the graph. Let's take an example. A body of mass 45 kilograms is pulled through a distance of 1.5 meters along a frictionless floor by applying a force as shown here. Calculate the force applied. This is a case where only a part of the applied force is used to do work. We know that work done is equal to force times distance. This force is equal to the weight of the box. So 45 kilograms times 10 newtons per kilogram to convert into weight times 1.5 meters. That gives us 625 joules. This work is equal to FD cos 30. So F times 1.5 times cos 30 is equal to 625. Get F, we divide both sides by 1.5 times cos 30. And we shall get force. And now let's talk about energy. Energy is quite simply the capacity to do work. Energy can be in lots of different places. It can be stored or it can be moving, but it is always the same thing. However, we give it a name depending on where it is, and there are basically 9 forms of energy, and most of them are fairly obvious. First is nuclear energy, and this is basically the energy of the sun. Second is thermal or heat energy, that energy that causes a change in temperature. Third is light energy, that causes a sensation of vision. 4. Sound energy. 5. Electrical energy. 6. Gravitational potential energy. 7. Kinetic energy. 8. Chemical energy, and this is the energy stored in chemical bonds. And 9. Elastic potential energy, and this is energy stored in something that has been stretched. One important thing about energy is that it cannot be created or destroyed. It can only be transferred from one form or place to another. This is known as the law of conservation of energy. For example, look at the fire again. We know that chemical energy is stored in the wood. And what is happening is that chemical energy is being transferred to the surrounding as light energy and heat energy. How about the light bulb? Here again, light and heat energy are being transferred to the surroundings, but this time it's electrical energy that is going into the light bulb. For a TV, electrical energy goes in. We get light and sound energy as well as some wasted heat energy. Finally, the slingshot. There is elastic potential energy stored in the stretched slingshot, and when released, that elastic potential energy is transformed to kinetic energy of the ball as it flies in the air, and also into gravitational potential energy as it gains height. We start with gravitational potential energy. Now, consider a body of mass m placed on the ground. The weight of the body is given by mg. To raise the body through height h above the surface, the minimum force required is its weight, mg. Considering the upward direction to be positive, the work done to raise the body through height h against the gravitational force of attraction is mgh. This work is stored in the body as gravitational potential energy. Gravitational potential energy is the energy an object possesses by virtue of its height above some relative position, usually the Earth's surface. If you lift a ball up in the air, you are increasing its gravitational potential energy as it moves further away from the ground. If you release the ball, that potential energy is converted into kinetic energy that we shall see later. The closer an object is to the center of gravity of the Earth, the less potential energy it has. It may seem strange to bestow an object with more energy just by lifting it into the air, but remember we must get rid of the casual definition of energy for a more scientific one. The gravitational potential energy of objects on Earth is equal to the mass of the object in kilogram times the acceleration due to gravity of the Earth times the height of the object above the ground in meters. The greater the height, the greater the energy, as this represents the work that can be done by gravity to produce the motion of a falling object. Next, elastic potential energy. Now, consider a block attached to a spring placed on a smooth horizontal surface, while the other end is attached to a rigid wall. The position where the spring is at rest initially is considered to be the mean position with no displacement of the spring. The spring is compressed and released. We observe the spring oscillates to and fro from the mean position. The displacement of the spring is always measured from the mean position. The spring here is under the action of a force known as the spring force, which always acts opposite to the displacement. When the spring is stretched, the spring force acts to compress it, and when the spring is compressed, the spring force acts to stretch it. This spring force is the restoring force responsible for bringing the block and spring back to the mean position. The spring force is perpendicular to the displacement x from the mean position. That is, F is proportional to x, or F is equal to kx, where k is the spring constant. When the spring is stretched or compressed, the spring force or the restoring force increases from 0 to a maximum F, meaning that the average force is equal to 0 plus F over 2, giving us F over 2, or simply a half F. We know that work done is equal to force times distance. In this case, distance is the extension x. So work is equal to the average force times extension. That is a half F times x. But from Hooke's law, F is equal to kx, and therefore work is equal to a half kx squared. This work is stored as elastic potential energy of the spring or any elastic object when stretched or compressed by a distance x. For example, a 4.5 Newton force compresses a spring by 3 centimeters. How much work is done in compressing the spring by 6 centimeters? We have force in x, 4.5 newtons and 3 centimeters. First, we find k. Force is equal to kx, meaning that k is equal to force over x. 4.5 newtons over 0.03 meters, that is 3 centimeters, gives us 150 newtons per meter. Now we can find the work done for 6 centimeters. Work is equal to a half kx squared. A half times 150 times 0.06 squared. That gives us 0.27 joules. Next, we move to kinetic energy. Now, kinetic energy is the energy a body possesses due to its motion. Consider a body of mass m acted upon by a steady force F. The body accelerates from rest to a final velocity v in time t, covering a distance s. We know that distance is equal to average velocity times time. Average velocity itself is given as initial velocity plus the final velocity divided by 2. The initial velocity is 0 since the body started at rest. So 0 plus V divided by 2 will give us V over 2. And therefore S, or distance, is equal to V over 2 times T, giving us Vt over 2. Work done is equal to force times distance. That gives us force times Vt over 2. This work is stored as the kinetic energy of the moving body. This means that a body in motion is able to do some work on another body. From Newton's second law of motion, force is equal to mass times acceleration. Substituting above, work will be equal to ma times Vt over 2. We also know that acceleration is equal to velocity v over time t. And so work will be equal to m times v over t times vt over 2. The t's cancel out so that we remain with mv squared over 2, or half mv squared. This is the expression for kinetic energy. Notice the presence of mass in the expression for kinetic energy. This means that if two objects with different masses are moving at the same velocity, the more massive object will have more kinetic energy. Now we move to work energy theorem. We know that the kinetic energy of a body of mass m moving with a velocity v is equal to a half mv squared. Consider a body of mass m moving with an initial velocity u and let a constant net force F act on it. At the end of displacement s, its velocity becomes v. We know from equations of linear motion that v squared minus u squared is equal to 2as. Multiplying both sides by a half m and simplifying, we get a half mv squared minus a half mu squared is equal to mas. But ma is equal to force F. So a half mv squared minus a half mu squared is equal to Fs. Fs is equal to work done. A half mv squared is the final kinetic energy, and a half mu squared is the initial kinetic energy. In simple terms, final kinetic energy minus the initial kinetic energy is equal to work done. Therefore, work done is equal to the change in kinetic energy. This is called the work energy theorem. Let's take an example. An object of mass 50 kilograms moves with a velocity of 11.2 meters per second. An event occurs where it transfers 1,539 joules of energy to another object as work. What is the new velocity of the object? Initial kinetic energy is equal to a half times 50 times 11.2 squared. That gives us 3,136 joules. Work done is equal to 1,539 joules. This is the energy lost by the object. So the final energy will be 3,136 joules minus 1,539 joules. That gives us 1,597 joules. We now apply the formula for kinetic energy to find V. A half mv squared will be equal to 1,597. A half times 50 times v squared is equal to 1,597. 25 v squared is equal to 1597. We divide both sides by 25. We get v squared is equal to 63.88. and v is equal to 7.99 meters per second. Next, conservation of energy. We now know about kinetic energy and potential energy, And we know that these quantities can be altered as an object moves, like the way potential energy is converted to kinetic energy when a body experiences free fall towards the ground. But energy can be transferred in a variety of other ways as well. So we must learn about these kinds of energy and how they can be transformed from one to another. We also understand that while energy can be transformed, the total energy of a closed system will always be conserved. As an object falls, the potential energy is converted into kinetic energy, but the sum of the potential and kinetic energy of the object will remain the same at every instance during the free fall. We call this sum the mechanical energy of the system. This is more easily visualized using the simple oscillatory motion of a spring system, which utilizes elastic potential energy. But we can also use a pendulum, which will use gravitational potential energy. At the top of the swing, the pendulum possesses its maximum potential energy and zero kinetic energy. The very bottom of the swing, it possesses its minimum potential energy and maximum kinetic energy. As these two forms interchange again and again, there is conservation of energy, and the total mechanical energy, which is the sum of the two, is constant. This can be expressed using this equation. If mechanical energy is the sum of kinetic energy and potential energy, which are in turn represented by these equations, and that this value is conserved, then a half mv squared initial plus mgh initial is equal to a half mv squared final plus mgh final. It shows the sum of the potential energy and kinetic energy of systems like the pendulum will be the same at each time in its motion. For example, a 25 kilogram object falling towards the earth has a velocity of 8.5 meters per second when it's 100 meters above the ground. What will be its velocity at 20 meters above the ground? So, the initial kinetic energy is equal to a half times 25 times 8.5 squared. That gives us 903 joules. Initial potential energy, 25 times 10 times 100 gives us 25,000 joules. Final potential energy is equal to 25 times 10 times 20, giving us 5,000 joules. According to the law of conservation of mechanical energy, 903 plus 25,000 will be equal to the final kinetic energy plus 5,000. So the final kinetic energy will be equal to 903 plus 25,000 minus 5,000, giving us 20,903. A half times 25 times v squared will be equal to 20,903. 12.5 v squared is equal to 20,903. We divide both sides by 12.5, and v squared is equal to 1,672.24, making v equal to 40.9 meters per second. Power. Power is the rate of doing work. That is, power is equal to work over time, or change in kinetic energy over time. But work is equal to force times distance. So power is equal to force times distance over time. Again, distance over time is equal to velocity, and therefore power is also equal to force times the uniform velocity. From the expression power is equal to work over time, it means the unit of power is joules per second. This is called watt. In certain machines like motors, you will see work indicated in horsepower. Years ago, before motors were invented, most work was accomplished manually. It was estimated that one horse could accomplish an equivalent of approximately 1,055 joules of work per second, and that is how horsepower was born. But in science, we use watts. Let's take an example. A 50-kilogram man climbs upstairs to a height of 6 meters in 8 seconds. Calculate the average power in doing so. Power is equal to work done over time. That is also equal to force times distance over time. 50 times 10 to convert into force times 6 divided by 8 gives us 375 watts. Now we talk about machines. Now, whereas many people oversimplify the concept of work and energy, when most people hear the term machine, they think of sophisticated and sometimes automated pieces of equipment. But machines can be as simple as a pair of scissors. A machine is simply any device used to make work easier. But machines do not reduce or decrease the amount of work done. Instead, they change the way work is done, usually by multiplying the applied force. In this chapter, we will talk about 6 simple machines: a lever, an inclined plane, a pulley, a screw, and a wheel and axle. But let's first talk about some common terminologies. Effort is the force applied to the machine. It is measured in newtons. Load is the opposing force exerted by the machine, and it is also given in newtons. Mechanical advantage is the ratio of the load to effort. Since it's a ratio of 2 similar units, mechanical advantage is unitless. Velocity ratio VR is the ratio of the distance moved by the effort to the distance moved by the load. It is also a ratio of 2 distances, and it is therefore unitless. Efficiency mu is the ratio of the work done by the load to the work done by the effort, expressed as a percentage. It is also given as the ratio of the work output to work input, expressed as a percentage. But work done is equal to force times distance, and therefore efficiency is equal to load times load distance over effort times effort distance. Load over effort is equal to mechanical advantage, and effort distance over load distance is equal to velocity ratio, meaning that load distance over effort distance is equal to 1 over velocity ratio. And therefore, efficiency will be equal to mechanical advantage times 1 over velocity ratio times 100, making it mechanical advantage over velocity ratio times 100%. So, first machine, levers. This is a simple machine that works on the principle of moment. The main parts are the effort arm, load arm, and the fulcrum or pivot. In order to achieve greater mechanical advantage in levers, we trade distance to get a larger force. This means we apply a small effort over a long distance to achieve a greater output force on the load, but over a short distance. For example, in this lever, the effort is 2 units from the fulcrum, while the load is 1 unit from the fulcrum. In this case, the velocity ratio is 2 over 1 or 2. In this lever, the effort applied will be able to generate twice that force on the load. But at what cost? Distance. The effort will have to move twice the distance moved by the load. So for this lever, the mechanical advantage is 2, meaning its efficiency will be 2 over 2 times 100, giving us 100%. Usually we do not have machines with 100% efficiency, and that is because some effort will be used to overcome the force of friction at the fulcrum. We take an example. A 20 Newton force applied 8 meters from a fulcrum is used to raise a 60 Newton weight placed 2 meters from the fulcrum. Calculate the efficiency of the lever. Efficiency is equal to mechanical advantage over the velocity ratio times 100. Mechanical advantage is equal to load over effort, that is 60 over 20, giving us 3. Velocity ratio is equal to effort distance over load distance. In this case, it will be 8 over 2, giving us 4. And therefore, the efficiency will be 3 over 4 times 100, giving us 75%. Depending on the relative position of the effort, the load and the fulcrum, levers are divided into 3 classes. In first-class levers, the fulcrum is between the load and the effort. You can see that the effort arm is much longer than the load arm. This enables the lever to multiply the applied force to lift a larger load. In this other first-class lever, the effort arm is shorter than the load arm. This will be more difficult to lift the load. You will actually need to apply an effort larger than the weight of the load, which will be very inefficient. A pair of scissors is an example of a first-class lever. Effort, fulcrum, and this is the load area. We place the load near the fulcrum to make the load arm shorter. Placing the cardboard here will be difficult to cut, but if we place it here, the cardboard will be cut much more easily as the load arm will be shorter than the effort arm. For a pliers too, the effort arm is longer than the load arm, making pliers very efficient in doing heavy tasks. In class 2 levers, the load is between the fulcrum and the effort. Here, the effort arm is the distance from the effort to the fulcrum, and the load arm is the distance between the load and the fulcrum. These type of levers are used to do heavyweight activities. Examples include a wheelbarrow, a lemon squeezer, a bottle opener, and nut crackers. Class 3 levers have effort in the middle between the load and the fulcrum. This is the effort arm, and this is the load arm. Here, the load arm is larger than the effort arm, so a larger effort is required to do a very small work. This type of levers are used to do very light jobs. Example is a tweezer, others are stapler and fishing rod. Next simple machine is wheel and axle. The wheel and axle is a modified form of the wheel in which a shaft or a wheel of a smaller diameter called the axle is attached to a larger wheel. Moving the wheel results in movement of the axle and vice versa. For instance, if you take a screwdriver and try to open a screw by turning at the shaft, it will be difficult. But when we open the screw by turning the screwdriver by the handle, it is much easier. This is an example of wheel and axle. The handle is the wheel, as its diameter is greater than that of the shaft, which is the axle. When turning at the shaft, we need to apply a lot of effort, and this is because of the small diameter. It is, however, easier to open using a handle of a greater diameter. So if you want to apply less force, you apply the effort at the wheel rather than the axle. and we can use a wheel of a greater diameter depending on the task. When do we turn the axle instead of the wheel? Consider this wheel an axle where the axle moves one rotation and the wheel does it as well. But when the axle completes one rotation, the distance covered is small because of its small diameter. On the other hand, one rotation of the wheel covers a larger distance compared to the axle. So moving the axle to a smaller distance results in a larger distance covered by the wheel. So again, we trade force for distance depending on what we need. The wheel and axle is used in bicycles where a larger force is applied over a short distance on the axle to move a longer distance on the wheel. A water tap is also an example of a wheel and axle. Without the wheel, it will be difficult to turn the axle. So we apply a small effort over a long distance on the wheel to move a larger load on the axle but over a short distance. The same happens in the steering wheel of a car. It is also used to lift heavy loads. In one complete turn, the wheel covers a distance equal to 2 pi r capital, and the load covers 2 pi r small. Therefore, the velocity ratio is equal to 2 pi r capital over 2 pi r small, giving us r capital over r small. The mechanical advantage is given by load over effort. Next, inclined plane. A ramp of any form is a simple machine and makes moving up and down of any load much easier. So you can slide down any heavy load or slide it up the ramp. The velocity ratio of an inclined plane is given by the effort distance over the load distance. That is equal to the length of the ramp over the vertical height. But sin theta is equal to height over the length, and therefore h is equal to L sin theta. And so velocity ratio will be equal to L over L sin theta, giving us 1 over sin theta. Next is screw. A screw is a simple machine that lets you join two things. It is basically an inclined plane wrapped around a pole. They can be used to hold things together or lift things. Just like the inclined plane, the longer the force takes, the less force is required to do work. Screws with more threads take less force to do a job since the force has to travel a longer distance. The distance between two successive threads is called the pitch of the screw. In one revolution, the screw moves forward or backwards through a distance equal to one pitch. The velocity ratio is equal to the circumference of the screw head over the pitch, that is 2 pi r over p. Next is pulleys. A pulley is a wheel with an axle where the edges of the wheel are grooved so that some rope can pass through this groove, and this rope is used to raise heavy objects. If one doesn't have enough strength to lift a heavy load, they can use a simple pulley. One end of the rope is attached to the object and passes through the groove, and the other end of the rope is free and can be pulled to lift the object. A pulley helps to reverse the direction of the pulling force. You pull the rope downwards to lift the load up. To lift an object 100 kilograms, you have to pull down with a force equivalent to 100 kilograms or 1,000 newtons. To raise the weight 1 meter into the air, you have to pull the rope through a total distance of 1 meter at the loose end. So a single pulley only changes the direction of the applied force and therefore doesn't give any mechanical advantage or make the work easier. To get more mechanical advantage, we increase the number of pulleys. Pulleys are of two types. They can be fixed pulleys or movable pulleys. Fixed pulleys are those with a pulley tied to a bar or beam and the pulley doesn't move at all when the rope is pulled. It just changes the direction of the force and there is no multiplication of force. It is easier to apply a force downwards than applying it upwards. In a movable pulley, the pulley is not tied to any beam or bar. One end of the rope is tied to a fixed beam or bar, and the other end is free to be pulled, and the pulley is at the center to which the load is attached. This way, the weight of the load is shared between the fixed bar and the person pulling the rope. It is a pulley that moves along with the load. The load moves in the direction of the applied force, and it takes less force to lift or move the object. And the more the number of pulleys and supporting ropes, the smaller the force that is required. So a movable pulley multiplies the force. Now let's see a compound pulley. Compound pulleys are also called block and tackle. It is a combination of a fixed and one or more movable pulleys. Whereas a single pulley only changes the direction of the applied force without giving much mechanical advantage, a compound pulley is able to reduce the effort required to do the work. For example, if the load weighs 100 newtons, a compound pulley reduces the lifting force to 15 newtons, so the mechanical advantage is equal to 2. Greater reductions are possible with more number of pulley wheels and longer ropes. Let's look at compound pulleys and the mechanical advantage they offer. We have 2 wheels and a rope looped around them. A 100 kilogram weight is equally supported by 2 pulleys and a very long rope. And because of this setting, you can lift it by putting a force of just 500 newtons instead of the required 1000 newtons. This compound pulley is therefore giving a mechanical advantage of 2. The 2 pulley system is multiplying the applied force by 2. However, the distance moved by the effort will have to double. The weight rises 1 meter, but the loose end has to be pulled twice that far. This gives a velocity ratio of 2. It means that if there is no friction, this pulley system will have an efficiency of 100%. How about a pulley system with 4 wheels? Here, we have a compound pulley with 4 wheels. So, 100 kilogram mass is equally supported by 4 pulleys and an even longer rope. This means you can lift it by pulling it with a force of just 250 newtons instead of 1000 newtons. So it's given us a lot of mechanical advantage equal to 4, meaning it multiplies the applied force 4 times. But again, the distance moved by the applied force is 4 times the distance moved by the load. Pulleys are used, for instance, in cranes to lift very heavy loads. Finally, gears. Gears are basically wheels with teeth, and they always work in pairs. The teeth of one gear interlock or engage with those of the other gear. Many gears joined together make a gear train. The driver is the first gear that starts the movement. The rest are called the driven gears. So gears transfer forces and motion from one object to another, making work easier and faster. Gears can change the speed and direction of a moving object, but not both at the same time. When two different size gears engage, mechanical advantage is produced. Different gears differ from each other in the way teeth are arranged. Spur or straight gears have their teeth straight and parallel to the axle of the wheel. Their main purpose is to transmit power and motion between two parallel shafts. They are the most common, easy to manufacture, but produce sound and vibration, especially at high speed. Helical gears are also called skew gears. Here, the teeth are not parallel to the shaft, but are rather inclined at some angle. They have more power than the spur gears and produce less noise and vibration. Their main function is to reduce speed. Bevel gears are used to shift power from one direction to another. They shift the force from one axis to the required axis. So they help in changing the direction of a moving object. Worm gears have a screw-like gear driving a big circular gear. They reduce speed but give more power or force. They can also be used in changing the direction of motion. A rack and pinion gear is made of a rack with other gears engaged with it. It changes the circular motion into linear motion. It is used in cliff and hill climbing and rack railroads, car steering system, weighing scale, and so on. In a gear system, if the driver wheel has N teeth and the driven wheel has N capital teeth, when the driver wheel makes one revolution, the driven wheel makes N over N capital revolutions. Velocity ratio is equal to the number of revolutions of the driver wheel over the number of revolutions of the driven wheel. This is equal to the number of teeth of the driver wheel over the number of teeth of the driven wheel. This gives 1 divided by N over N capital, giving us N capital over N small.